Okay, so the first case study we're going to look at treatments for leprosy. So leprosy is a type of bacterium. What it does is it gets into the nerves and causes destruction, and because it causes destruction of the nerves, you get sort of like necrotic lesions on your fingers and toes, etc. So in this particular thing, we've got two drugs we're going to look at for leprosy. It's a randomized trial. We've got 30 patients in total, and they're randomly allocated to drug A, drug D, or control. And what we measure is a response variable Y, which is a score representing how abundant these bacilli, the leprosy bacilli, are over 6 sites in the body. And also we measured it beforehand. So we measured before we even gave them the treatment, this sort of abundance. Let's just clean that up. So let's first of all read in some packages. And let's have a look. Let's read in this data, and here we've got it. We've got our treatment, our X, which is a measure of abundance of the leprosy bacilli before the treatment, and then a measure after the treatment. So we'll do a quick EDA. Not a lot to see here. There's no missing data, which is good. We've got a mean of X of 10.7, then 7.9, so it's gone down. Standard deviation 4.79, 6.67, all good. Let's just check that we do have the information we've got. So how many in each group? Yep, 10 in each group, 30 in all. So first of all, let's have a look at this abundance. A little bit right skewed, not a lot of data, hard to see any patterns here, but we've definitely got a peak up about here. And let's have a look at the treatment. So yeah, we definitely see that we have more abundance of leprosy on the control compared with the two treatments. The treatments seem to have an effect and dropping down the amount of bacilli, which is what we want. We'd like to see less bacilli because it means it's getting rid of them. So let's just do a simple model. We're going to do the number of bacillus on the treatment. So let's do that. Have a summary. Looks like we've got a significant difference of both A and D compared with the control, which is good. Because we've got a categorical, we look at all that information in one go. And yes, we've got a nice significant effect of treatment. All looks good. But you know that's not going to be the case. You don't have a whole case study in week 10 of a stats modelling course if we can just do a simple ANOVA like that. So what's going wrong? Why am I worried? Well, the first thing you should always do, if you've got extra covariates, in this case our X, and what do I mean by covariate? I mean an extra measurement that we could put in our model. That's all I really mean. Often we take our predictors and we split them into treatments and the other stuff. And the other stuff is often called a covariate. It's something that varies along with what you've got. And we've got this extra covariate, this X. So we should investigate it. We should just have a quick look. So the first thing I'm going to do is I'm going to have a look at treatment between them. And we've got a bit of a concern here. So these are the abundance of the bacilli before we did anything. These are just what we looked at. Now, because of randomization, they should all be about the same, but they're not. Look, the controls seem to have a lot more bacillus than the other two to start off with. Now, that could just be random chance. Or maybe they didn't randomize it properly. I don't know. I don't have the information, but I'm worried. Because ideally, if you think about it, whenever you're in an experiment, you would like all the subjects to be as equal as possible, except for the treatment. And here, they're not as equal as possible. The controls have more leprosy to start off with. So this could affect the things. Is that a significant effect? It looks quite good. Well, what we can do is we could quickly do a linear regression where we say, is there a significant difference between X for treatment? So we can again have a look. Doesn't look too bad. So even though we're seeing those differences in our side-by-side box plots, we're not seeing it in the model. But we should incorporate it. So what I'm going to do now is I'm going to say, let's do a simple parallel regression. We've got our Y is our leprosy after the treatment. X is a continuous variable. That's how much leprosy before the treatment, and then we've got the treatment. So we're just doing, if you remember, a parallel regression. If we run this, yes, we have a significant effect of your previous leprosy, but now our treatments don't seem to be significant. They've now got 0.07, 0.08. If we do our ANOVA, yeah, the treatment effect is gone. The biggest predictor of how much leprosy you'll have after the treatment is how much leprosy you had before the treatment. And the only reason the treatments looked so good was there was this difference between them. In fact, we can actually compare and say, well, which is the better model? And if we go and look at, for example, AIC, we can see that model 3, the one that has both the treatment and the previous leprosy in there, is more significant. The R-squared, you can explain a lot more of the R-squared. So the biggest predictor of leprosy is leprosy you started off with. And what we'll do here is we'll do our parallel regression plot. Actually, I've done separate individual ones. And you can see the biggest predictor of your leprosy after any treatment is your leprosy before. And in fact, what we'd like to see is a significant difference between the intercepts, these various things, if treatment had an effect. I'm not going to do that. I think it's just an interesting example of you've got to be really careful jumping to a conclusion. In this case, the covariate that was important was the one beforehand. So how could we actually see if treatment has an effect? Well, there's different ways you could do it. You could do the interaction model. You know how to do that already. You've done a COVID before. Instead of putting the plus in that X and treatment, you could put the multiply. Have a go with that if you want. I'm going to do a slightly different way. I'm going to look at differences. I'm going to say, what's the difference between what you started off with and what you ended up with? In fact, let's change this so we'll find out. Now that make it quite good. X minus Y is what we want because the D now will be positive if you have an effect. So there we are. Now we'll look at treatment. And we see there is more of a difference. What this means is, because this is positive, is these are getting rid of the leprosy. Is it a significant difference? I don't know. We're going to have a look. So what I've done here is what we're doing is we have here what we call a repeated measures data. What I mean by repeated measures is we measured the same thing, in this case leprosy abundance, and we've measured it twice for each subject. What, time point 0 before the treatment and time point 1 after treatment. So we've got this repeated effects. And so there's different ways you can actually treat this. The simplest way is what we're doing here is we're just going to calculate the difference for each person, and that will take into account the correlation within each person. So now we're going to do a regression of difference on treatment. And you see, it's still not significant. So we do see that the treatments seem to be helping a little bit, and maybe with more data we'd see a stronger effect here, but it's not significant. And finally with ANOVA, not significant. So what's the take-home message with this? Well, first of all, if you measure things, be very, very careful to incorporate in the model, or at least explore them. 2, when you do randomization, it's a good idea to do some sort of post hoc check to make sure it was randomized. In this particular case, you saw it wasn't, that the controls ended up just by chance with more leprosy than the other 2 groups. Or maybe it wasn't by chance, I don't know. As I said, don't know the data. But I think the main thing is, when you have these covariates, explore them, put them in your model, see what effect they're having, because you might be getting a false treatment effect. Okay, all good? Next time we'll explore lung capacity. See you next time.